As we go through this course, we're going to talk about a lot of different properties and measurements we can make on matter. Remember, matter is just anything that has mass and occupies space. So everything around us, even the smallest of gas molecules. One way we will measure matter is through the use of mass. Mass is the measure of the quantity of matter, how much we have, whereas weight is a measure of force. These terms tend to be used interchangeably, but they're not actually equal to one another. We can talk about a conversion factor between mass and weight, but that is assuming that we're on Earth. There is a conversion factor if we were on the moon, but it's a different conversion factor between the two. So when we're talking about the quantity of matter, we want to talk about its mass. Sometimes we also talk about the volume of a sample. Here are some common geometric shapes and some formulas for them. Now, you're not expected to memorize the formulas for the cylinder or sphere or any of the other shapes. You should know for a cube or for a rectangular prism, which is just length times width times height. If you need to use the other formulas, they will be provided for you either on the exam or you can look them up online for homework. However, you should know how to use the formulas. Another value we report for substances is density. If we look at our picture here, we see that we have many different substances mixed together. However, they separate out from one another based on their density. The most dense substance at the bottom, the least dense substance at the top. Density is just a ratio of mass and volume. So density equals mass over volume, and we can use this to compare different substances. This is an intensive property. It doesn't matter how much we have of something, its density remains the same. If I take a sample of water at room temperature, it doesn't matter whether I have 2 milliliters or 2 gallons or 2 tons of water, I'm still going to have the same density. We can also measure the energy of different processes. There's always an energy change when we look at any process. Energy can be gained or lost. In this picture, we see examples of different types of energies, so from a reaction happening per atom to an earthquake and everything in between. There are two units we typically use when we're talking about energy, either calories or joules. And just like many other values, there's a mathematical relationship between those two values. One thing we want to be careful to note is that whether or not we put a little c or a capital C, it makes a difference in the value of that unit. 1,000 little c calories is equal to 1 big C calorie. It's actually a kilocalorie, and the numbers you see on food packaging are actually kilocalories or big C calories. Another property we can talk about is specific heat. This is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. We see some examples listed here, and we note that water at 1 calorie per gram degree Celsius is actually a very high value. Looking at something like silver or gold, we have much lower values. This means it takes less energy to heat them up, but it also means they won't hold the heat quite as long. When I look at water, I see it takes 1 calorie per gram per degree Celsius. If I go to the ocean, I note that the sand, which has a much lower specific heat, heats up fairly quickly. If I go out to the beach around 9, the sand feels cool. I go back at 2 o'clock, the sand feels very hot. However, the water doesn't change temperature all that much because it takes more energy to raise the temperature of the water by even just 1 degree Celsius. As a result, the water also holds that heat longer. It takes much longer for the water to cool off, whereas if I go back to the beach at night, I'm going to note that the sand is again cool.